So good
Glad to
morning,
be here
everyone.
with you. Yeah, please, you can proceed with your talk. The rest of the speakers, please mute your speakers. And now I'd like to announce the first talk. The title is Machine Learning Techniques for the AB Initial Bravais Lattice Determination by speaker Inma Conde, University of Sydney, Australia. Please go ahead.
Thank you for the presentation. Good evening, everyone from Australia. This is in the evening here. I wish I was there in Paris with all of you. It is an honor to be part of this conference and talk about AI, which is a very important topic. So my topic is called Machine Learning Techniques for the ab initio Bravais lattice determination. And I am one of the co-authors for this article, which was published. And I am actually the most junior researcher for this research. I come from the University of Sydney in Australia, and I'm going to explain a little bit about this research. So artificial intelligence is based on a series of algorithms that seek to mimic or emulate how our brain and central nervous system process information. The processing unit is a cell called the neuron. From the cytoplasm, a series of branched connections called dendrites emerge, and a wider connection that links one neuron to another is called an axon, as you can see here in the picture. Communication occurs through electrical signals known as synapses. So let me continue to the next slide. So we have here neural networks. So you can see here how each node in the network represents a neuron. Neurons are grouped into layers, and there is always an input layer where information is received, and another output layer where information is output. And a number of intermediate layers are called the hidden layers. So how the neural network functions. So in the figure, each node represents a neuron, has a set of dendritic inputs and a single axon output. Weight factors, as you can see here, WI1, 2, weight the inputs. The node sums all entries where the function passes, weighted by these factors. Initially, weight functions are random. Moreover, the axon has an incorporated activation mathematical function that has a sigmoidal S-shaped shape. In the figure on the right, the input layer receives a series of information that has a sigmoidal S-shaped shape. At the same time, it provides the results. As the weights are random, we don't know the weights exactly, the processing or calculated outcome doesn't match the ideal or expected value. Then via a backward mechanism, backpropagation, weight functions are corrected until the optimal accuracy between the calculated and expected results achieved. So let me pass to the next. Yeah, here we go. Well, so what can we see here? This is just a neural network example. Here is a simple, very simple example of a neural network. The input layer has 8 nodes because 8 inputs or attributes are expected, and the output layer has only 4 nodes because 4 results are expected, and a single hidden layer has also been added, which also has 9 nodes in total. This is what is known as a topology of 884. So now let's pass to crystallography, which is the topic of the research in the field. So in crystallography, there is a fundamental problem of identifying what is called the Bravais lattice. Since all crystals have translation symmetry, the unit cell must belong to one of the 7 crystal systems. And within each crystal system, there are different ways to form what is called the Bravais lattice. This is a geometric locus of the points in space where Bravais postulated is satisfied. It can be seen how there are 7 crystal systems, but 14 Bravais lattices. Identifying the Bravais lattice from X-ray diffraction spectra, it is actually indeed a very complex problem. We attempt to address it through machine learning algorithms. So here is what you can see is what is called an X-ray diffraction. So our source of information can be seen here. This diffraction spectra satisfy what is called the Bragg's law. In this spectra, the wavelength is monochromatic and known, we know. The angular positions of the diffraction peaks provide us with the Bragg angles. Therefore, they allow us to determine the other variable known as interplanar spacing or interplanar distance. The problem of reconstructing the Bravais lattice from a few dozen interplanar spacing is of actually great complexity. So we can see here some mathematical relationships. So these mathematical relationships link lattice spacing for each crystal system with the geometric parameters defining the crystal cell. And here we can see what is the X-ray diffraction patterns. There are no predictable patterns in this figure, and there are 2 X-ray diffraction spectra that belong to the same Bravais lattice. As you can see, orthorhombic primitive, and yet it can be seen that the spectra are very different. So let's have a look at the classification of the problem. So our problem boils down to a classification problem. In the left box, as you can see, we have assigned a code of from 1 to 13 to each possible Bravais lattice, excluding the 14th because it is a hexagonal and trigonal networks could refer to the same type of unit cell. So it's only 13, even though there are 14. Therefore, hexagonal and trigonal are in number 13. Classes 6 and 11 also correspond to primitive, orthorhombic, and base-centered monoclinic, which is also important. For training, a very careful job has been done on the databases for training, 500 different materials, which have been chosen for which the Bravais lattice is known. So we know exactly for these 500. However, as these are experimental results, the distribution is very uneven across the 13 classes, with some classes having a very high number of instances and other less because they correspond to asymmetrics or Bravais lattices that are rare in nature. In other words, the distribution of the initial data is not balanced. So in the machine learning tools that we have used to solve this problem is the Weka platform that is from the University of Waikato and in New Zealand, which Weka is the one bird from New Zealand. The structure of the input files is very simple. The first 20 lattice spacing are chosen, and then the lattice spacings have a monotonically decreasing behavior. To normalize this data, each sequence of 20 spacing has been divided by the first one of this by the largest, so that our normalized losses data. So in this slide, machine learning algorithms, 6 classifications algorithms have been tested corresponding to different categories, as you can see there. Naive Bayes respond to the Bayesian classifiers, Fourier belongs to fuzzy classifiers, and meta-estimators, which are the last category. So now let's pass to the model evaluation. The mathematical models used are the MVP, the multi-propagation neural network, and other machine learning models. Process results have been divided into 2 categories: the trend split 2/3, 1/3 technique, and tenfold cross-validation, where all data is divided into 10 groups, 50 each in all possible combinations, and for each case, 9 groups are used for training and 1 group for testing. In any case, it can be seen that The original data is not pre-processed, and there is a serious problem of imbalance. So what's happened? We're looking now at the pre-processing. When the pre-processed the initial data using two algorithms included in WECA, named SMOD and class balances. SMOD is the single minority oversampling technique, and balances and corrects the imbalance problem. It achieves an expanded data set where all classes are relatively well balanced. So here is the model performance. As you can see here, MVP has been discarded because the results are very poor. Statistics, you can see how the class balance and SMOD. Yes, sorry. MVP has been discarded because the results are very poor. K-statistics is the probability that hits were not random. It can be seen that the random tree method, which belongs to the meta estimators family, achieves an accuracy rate of 95% for the data, and the probability that this did not happen by chance is 93%. So in this kind of bar graph, you can see on the x-axis, on the y-axis, the results of the split Tuesday 1/3 in the test, and the CV are the cross validation, and indeed you can see that phase 5 random tree achieved the best results here. So number 5. So challenging the validation, we propose a challenge to validate our methodology, an infringement spectrum corresponding to tantalum doped zirconium oxide, which corresponds to a completely unknown structure. By the physical algorithm themselves, it was possible to assign the Bravais lattice having two possibilities. The possibility above corresponds to a primitive orthomorphic lattice, which was class number 6, or to a monoclonic centered in the bases. Finally, it could be known by physical methods that the validated solution was the one above, primitive orthomorphic. The only way to break the ambiguity is that the material was piezoelectric and ferroelectric, which is incompatible with the second type of the Bravais lattice. So let's quickly go to the confusion matrix. The most important results are shown in what is called the confusion matrix, which is this one. The first line, the 13 Bravais lattices are lattice from A to M, and the classification results ranges from 1 to 13. If I look under column A, there were 27 plus 1 minus 28 materials that belong to a class A. 27 were correctly classified in A and 1 erroneously classified in 2. And in column C, there was 36, so all were correct. The main diagonal, as you can see from A to M, A1, B2, C3, D4, has true positives, while the elements of the main diagonal are those that have been misclassified and appear as false positive, as you can see in A2. So finally, we did a very severe test. We adopted as a null hypothesis that the crystal belongs to the base-centered monoclonic class and should therefore be found at the position here. Yeah. So here you can see that it should be in the position column K and row K. And yet it can be seen how the classifier has moved within the K file, but the F class. Then it has been a success because the test is very hard. Initially, what we attributed to a position 11, as if it were base-centered monoclinics. So we're trying to test it. But it has moved actually to row 11 and column 6, which is the adequate one. So as a quick conclusion, and sorry it's taking me a lot, and I have this person with me, our approach using machine learning algorithms, particularly through the random tree method, shows promising results in identifying Bravais lattice from X-ray diffraction data. Challenges remain in handling datasets imbalances and ensuring robust classification across various crystal structures. Future work includes refining the model with more diverse datasets and exploring advanced techniques to improve accuracy and reliability in crystallography classification. And I just wanted to say thank you very much. Please, you can see here my email. Send me any question or anything. And I want you also to check out our last AI publication, which is called Signal Processing Analysis for Detection of Anomalies in Numerical Series, which is in a very good journal, Space System for Organization. Thank you very much. If you have any questions, please, this is your time.
Any questions?